We'll talk about black box testing in a second, but first I want to correct something I said earlier. Um, I told you that the solar system is only 2 billion years old. Well, in fact, I looked it up, and scientists think that the solar system is probably more like 4.6 billion years old. And in about 5 billion years, it looks like the sun is going to expand to more than the size of the Earth's orbit and eventually burn out. And so that'll happen in about 5 billion years. So we're about halfway through the lifetime of the solar system. But it's, in fact, 4.6 billion years old. Sorry for the misinformation. It reminds me of a story. The famous astronomer was giving a talk one night, and this lady comes up to him afterward and said, "Pardon me, did I hear you right? How long did you say that it was going to be before the sun explodes and the Earth is just totally destroyed?" And he said, "Oh, about 5 billion years." And she said, "Oh, thank goodness. I thought you said 5 million years." Okay, now to the lecture. In black box testing, we can't test to the structure of the program, but in fact we have to test to the set of the requirements for the program, for example, or what we refer to as the domain of the program. So this is sometimes referred to as domain testing. Now, what do I mean by domain? If we think of the program as a mathematical function, then it maps inputs to outputs, or maps points from a domain to points in a range, right? If you remember from set theory. Let me draw a diagram here. So that's the domain of the program. And the whole function of a program is to map elements from the domain into elements of the range. So a point in the domain maps to a point in the range. Another point in the domain maps to another point in the range. As a matter of fact, you can have multiple points in the domain mapping to the same element in the range, as we pointed out before in a function. Okay. What you can't have is an element in the domain mapped to more than one element in the range. That would not be a function. Okay. So what we want to look at when we're examining the domain of the program, blow this up a little bit. So that's the domain, is what are the set of values that are like input to the program. That's the domain of the program. Well, suppose I have a program that has just one value. It's a Boolean. Then how many points are there in the domain? Well, there are two. One where the value is true, one where it's false, right? So that's two values. Suppose I have B is of type Boolean, and I have C is of type character. And these are byte characters, so that's 256 values. Now, how many different combinations of B and C could there be? Well, for each character, there are 256 different values of C, and then for each one of those, there would be 2 values of B. So the number of combinations of B and C would be 512. So it would be 512 points in the domain. Okay, what would one of those points be? Well, that one point might be the character X and the value true. Okay. Another point in the domain might be the character C and the value false for C and B. Okay. All right, so still, now there's only that's 512 values, right? Well, suppose I throw in another variable here. Let me call it A. And it is an integer, just integer. It's integer. Okay. Now how many values are there? How many combinations of values? Well, here's one. So it would be C, false, comma 1. Here's another one. C, false, comma 2. Another one, C, false 3, 4, 5, minus 1, minus 2. As a matter of fact, how many values are there in the domain now? How many points in the domain? Well, let's see, how many integers are there? There are like 2 billion integers. 2 billion integers, and we already established that there are 512 of that. So there are 2 billion times 512. So there are 1024 billion points in this. Or in other words, it's 1 trillion points in the domain. Big domain. So you can see it's going to be hard to test every possible, have every possible input to the program and completely test the program. So once again, we have to choose a subset. So what we do is we choose the subset of inputs that will be most likely to cause the program to fail, if we could figure that out. Well, a common technique for doing that is called equivalence partitioning. So what we'll do is we'll take the domain and we'll divide it up into pieces. Okay, so the pieces are called equivalence classes. So I've got my domain up here again. So a whole bunch of points in the domain, but we'll divide them up into pieces. Now the rationale for dividing the domain up into pieces is we'll put in the same partition of the domain all the pieces that cause the program to do the same kind of thing. So there's a partition that all of the points in that partition will cause the program to do one thing. All the points in this partition will cause the program to do some other kind of behavior. So we can describe those kinds of behaviors and partition the input sets, the domain, in other words, up into these partitions based on some sort of behavior. So you're carving the domain up into partitions. And it's called, each partition is sometimes referred to as an equivalence class, where all of the points in that partition of the domain cause an equivalent kind of behavior. Now, you could still have a lot of partitions, right? So what we'll base our partitions on, usually when we're doing this equivalence class partitioning, is a similar kind of externally visible behavior. So what we'll do is we'll analyze all the external conditions and we'll identify valid conditions, in other words, values of the input variables that cause the program to run properly, and then we'll identify some invalid conditions, values of the input variables that would cause the program to fail. For example, if the data type for a variable was a range of values. Now, suppose the variable was data type integer. Well, usually when we declare something to be a type integer, we really don't expect it to be able to have all possible 2 billion possible values. As a matter of fact, frequently the variable will have an expected value in some range, and if the value of that variable falls above the range or below the range, it'll cause a problem, and the program would fail. So what we look at is the legal range of values for the variable, and we'll devise a test case where one of the values was in the range, so then that would be a valid test case, and then we could choose a test case that has a value of that variable that's above the range, and that should cause the program to fail, and we'll choose a test case where the value of that variable is below the range, and that should cause the program to fail. Similarly, if the variable represents if there's a number of things that are supposed to be input, so we're expecting, say, a bunch of pulses or something like that, and what we're expecting is a number of pulses, then you choose a test case that has the correct number of things, and then a test case that has too many and a test case that has too few. The one that matches the number that test case should pass, and the one that has either too many or too few items should cause failures. If the value is to be selected from a set of legal values, then probably you're going to need an equivalence class for each valid element in the set, and choose a value that's not in the set for an invalid equivalence class. And if you have some sort of condition that specifies some sort of a Boolean that has to be true, then you choose a test case where that condition is true and a test case where the condition is not true. And now it is possible to incorporate all of the valid test cases in one giant test case. And this program should, if you run that set of initial conditions, the program should run properly and you shouldn't get a failure. And then what we can do is we can vary one variable at a time to cause it to have an invalid value. Choose a value for that variable from the invalid equivalence classes. And we do it one at a time because you don't want to change too many things, and because sometimes these erroneous input checks can mask each other out, and so you want to vary one thing at a time. So one valid test case and a whole bunch of invalid test cases. Here's an example. Back in the old days, before they ran out of area codes, the phone numbers had this structure. Area code was a 3-digit number between 201 and 905, and the first and last digit had to be non-zero. The next 3 digits had to be, well, it could be any 3-digit number. The suffix was a 4-digit number, right? And suppose in this little example, after you put in the phone number, you have to put in 3 pound signs and then one of these commands. So that's the input. So you can see what the domain of the program looks like, right? It consists of an area code, a prefix, a suffix, 3 pound signs, and a command. Well, for the area code, it is a range of values, plus there are conditions. And for the prefix, that's a range of values. Suffix is a range of values. The pound signs, there have to be 3 of them, 3 pound signs. And the command is taken from a set. So let's look at some valid inputs. A valid area code would be 301. A valid prefix is 345. That works. A valid suffix 6789. That works. 3 pound signs and one of the valid commands. So if we ran the program with that set of inputs, it should work fine. It should do the proper thing. As a matter of fact, we should probably choose a test case that tests each command, at least, right? So we'll have one valid input test case for each command in our set of commands. But now if we look for invalid test cases, we can vary each variable one at a time. So we can vary the area code, for example. We could have a test case where the area code is equal to 333, or a test case where it was 101 or 909, something that violated either the range or the condition. And do the same thing with the prefix. Those are some invalid test cases. And you can see you can change. So you can take your valid test cases and change one of the values of one of the variables to one of these illegal values, and the program should fail in those equivalence classes. Now, they've discovered that programs fail more frequently where the values of variables reach the edge of what they call the boundaries. For example, if the variable has a value selected from a range of values, if the legal values are in a range, like 1 to 100, then the program is not as likely to fail if you choose 50 as if you choose like 1 or 2 or 0 or -1 or 99 or 100 or 101. Okay? If you choose values for these variables right near the edges of the range, then you're more likely to get erroneous behavior. So you get the typical like off by 1 problem. And so what we'll do is we'll choose our test cases right at the boundary. So if the value is from the data type of the variable is from a range, then you'll choose 4 test cases. One is the minimum value, you choose one for the maximum value, and those should be good, those should work, right? And then choose one less than the minimum and one more than the maximum, and those should cause the program to fail. Now, if the program fails on when the variable has the minimum value, then you've got that off by 1. Or if it runs properly with one less than the minimum value, then it didn't check properly for that value. So this is called boundary value analysis, recognizing the fact that programs are more likely to fail if the values of these variables is sort of around the boundary, around the edges of those partitions of the domain, the equivalence classes. Now, if all that that'll find a lot of the defects in the program, but there's a large class of defects that are not can't find with either white box or black box testing, and this is what we sometimes call error guessing. It's other things that we could use to cause the program to fail. And a lot of times, you probably know some of these people. We seem to have these in every large company. The person that you go to come up with some test cases that will cause the program to fail that nobody ever thought of, because we're all too organized, and we're trying to use techniques that we've looked at here for doing white box or black box testing. But you got these people that work at these companies, and you take the program and say, hey, we'll give it to Harvey, because Harvey just seems to know the right kind of inputs to put in here into the programs to make them fail. And so he'll sit at the keyboard and he'll devise some inputs, cause the program to fail. And you say, well, how'd you come up with that? And he can't explain it. It's just a talent that he has to be able to divine these kinds of inputs. It's what I call error guessing. He's just somehow is able to come up with the right set of inputs to cause the program to fail, and it's not a scientific technique at all. But it's ways of testing the software that's not related by to the other methods, but it usually has to do with things like overlooked or missing requirements, where you misstated something, or you just completely forgot about something, and Harvey is just able to find it. He's able to find all these old mistakes that you made. Another type of testing is called idiot proofing. Idiot proofing is where you thoroughly test this product, because who knows what kind of inputs, what kind of users we're going to have. Normally, when we test a program, we test to expected kinds of inputs. But suppose this program was run by a bunch of monkeys, the proverbial bunch of monkeys. Then they could produce all sorts of weird inputs that we'd never expect. And if it's a robust program, if we intend for this to be a robust program, then we should test all possible crazy inputs. It's called idiot proofing. And I got a great quote here. Programming today is a race between software engineers striving to build bigger and better idiot-proof programs, and the universe trying to produce bigger and better idiots. So far, the universe is winning.